robot competitions require every team to build their own robot from scratch, which for a boat competition pretty much means you need a naval architect on your team. But not every university has a naval architecture program, so some teams can start off at a disadvantage.
But the Maritime RobotX Challenge is different. Each team is given the same basic boat platform, so they all start from a level playing field.
And the boat they get is the ocean-going equivalent of a race car, the futuristic WAM-V from Marine Advanced Research. To meet these boats, let's start with the designers.
The WAM-V is a very unique and capable craft. It's designed to ride basically on top of the waves. It's a very soft presence, but it has a suspension system and articulation system that allows the vessel to move with the waves, but that center platform stays completely stable. So it's a great platform for sensor packages. Works really well in this sort of competition where you want an elevated platform so you can deploy your sensor packages, but then at the same time you have a very stable vessel that can handle bigger waves.
The competition is actually very interesting because you have all these people, all these young people that are going to focus on a problem that is actually very difficult. I mean, the fact that you have to have a boat which is not controlled by somebody through the radio, but it's actually totally autonomous.
The boat is just a starting point. What the teams choose to do next is what distinguishes each entry dramatically. They need to develop the propulsion, sensing, computing hardware, and software that will turn that cool boat into a genuine robot that can run the course all by itself.
And all those decisions turn identical catamarans into very different roboboats. Let's find out what choices the different teams made as we meet the robots.
A lot of the students that we have here compete in all numerous AUSA Foundation collegiate competitions that are hosted. So when we set out to do this project, we set out with the goal in mind that we would end up with a platform that was sales ready, rugged, and reliable.
We aim for sort of modularity and controllability. This means that as the competition progresses in future iterations, if we need to add more systems to it, we simply build it into a nice new waterproof box, mount it on top, route a power cable to it, hook it into the boat's onboard network, and away we go.
Originally, we took a lot of the original sensors from the DARPA grant challenge that MIT took part in around a decade ago, and we augmented it with a few other sensors, especially our new Velodyne HDL32E.
In our limited situation, we did the best, like task 1 and task 3 and task 5. We made it, so we are very proud of ourselves.
Our boat is relying solely on the vision, and that is much harder than we originally thought. So we are pretty much trying to achieve all the tasks related to color and obstacle avoidance. We will also attempt to do that, but the thing is that it's much harder with vision than with lasers, which other teams have.
We made the LRF mount. It can swing LRFs, 3 LRFs, in order not to miss the object. Because the LRFs can see only on the horizontal line, so we should adjust the angle to not to miss the object.
First, we had to analyze the missions and thought about what we need. And then we've analyzed each mission detailedly. And then we thought the most important thing in for our competition is navigation and mapping. So we focused on that.
Our first thoughts were we really wanted to get the boat on the water and see how it handled as fast as possible, so we went with a really low-cost initial propulsion solution, and that sort of allowed us to get out on the water within a month of receiving the boat and get a lot of testing done early.
In terms of our process, we really started from the regulations that were given to us, and the first step was really to meet the regulations. From there, we slowly built the boat, and then, it was really regulation guided.
These practice days, we are every day changing our sensors, our image processing. Web camera, which is often used Skype or something. And next, we are using omnidirectional camera that can search 360 degrees. And maybe in these 3 days, we will use Kinect or something.
I think we've got some very advanced algorithms. We primarily work in, as I mentioned, autonomy and so forth in the research group at Flinders. All we're hoping at this stage, I think, is that we can get some of the lower level problems sorted out so that we can demonstrate our high level capabilities at this competition.
Our system has hydrophone arrays because in this competition it is important to find the underwater beacon because it is very difficult to spot and then it is a high score.
We have also some plans for the future to use this boat for monitoring marine life, to let the boat run and to put more sensors to detect things underwater, etc.
Definitely we're well prepared. I mean, this is home ground advantage. We know that Singapore is going to be really hot. So in fact, for heat dissipation is one of our main key considerations for the box design. You can see that we have UV-proof box and we have some ventilation going on to keep the temperature down so that electronics can work properly.
One of the main things that we love about this platform is that there's so many applications for it. We have a number of PhDs and graduate students that are working on different areas of research with this platform, not just for this competition, but for things outside of it and in a lot of ways a lot more complex. Villanova, our partner university, also has the same system in effect.
You can find out lots more about each team's boat by visiting the team's website. They all had to make one as a part of this competition.
And for those teams that perform well enough to earn a spot in the finals, you'll be able to ask technical questions in real time during our live finals webcast. You'll find links to all of these at robotx.org.